right, good morning. Thanks for joining us in this session. The session is about demystifying attestation. Quick show of hands before we get going. How many of you here are familiar with confidential computing? Okay, that's good. How many of you are using confidential computing in AWS? That's good. That's good. All right. So this talk is going to be about measuring and verifying your execution environments, very specifically trusted execution environments, right? So we're going to be talking about a lot of confidential computing, securing your workloads, specifically securing your generative AI workloads as well. We have a cool little code walkthrough that we'll do later on. So let's actually get going. My name is Sudhir. I'm a specialist solutions architect. My focus area is confidential computing. Been with AWS for about 4 years now, doing this and did a few other things as well. With me, I have Suresh. Suresh.
Hello, everyone. I'm Suresh Viragoni. I'm a specialist solutions architect as well for GenAI. I work with our LLM providers like Anthropic, DeepSeek, etc. So we work together, like we are cross-team. We work together to put together a real-world use case in GenAI on how to protect your data and assets like code or model weights, etc. And in this one, we will kind of walk you through the code, like Sudhir mentioned. Yeah.
Absolutely. Thanks, Suresh. All right, so let's get going. It's a packed 1 hour agenda here. We'll start off with a very, very brief introduction to confidential computing, right? And then we'll move on to the types of trusted execution environments, the options that you have available on AWS. And then we'll jump right into code, right? I promise we'll keep the slides to a bare minimum. So let's start with confidential computing. This is very important to understand because AWS's perspective of confidential computing is a little bit different to what you may have heard already. Our perspective starts with what we like to call dimensional model, right? So what I have on the screen here are two dimensions, dimension 1 and dimension 2, right? And the way we arrived at these is through talking to customers like yourself. And when we talk to customers, they primarily asked us, with respect to confidential computing, is, hey, we need two things, basically. Number one, dimension 1 is where customers have asked us, I need assurances that AWS, as a cloud operator, cannot peek into my data and code, right? And dimension 2 is where customers like yourself have asked us that, hey, I need mechanisms, tools, service features where I can further isolate and segregate my workloads into confidential computing, into those trusted execution environments, right? So those are the broad two dimensions. Before I get into the answers to those dimensions or the solutions for those dimensions on AWS, let's try to define what confidential computing is, right? So confidential computing for us at AWS is the use of specialized hardware, firmware, and software to protect data and code while it is being operated upon. The important term here is while it is being operated upon, right? Because protecting data and code in transit and at rest are mature constructs. You're probably already doing this in today's world with your normal workloads, right? No need to look at confidential computing for this. Those are things like on-envelope encryption, using key management systems, HTTPS, TLS, things like that, right? So that's the reason why confidential computing is all about protecting while it is being operated upon. So what do I mean by that? I'll give an example. And before we go into that, right? Dimension 1, if I just go back to the previous slide, the answer to dimension 1 of confidential computing, where customers tend to see AWS operator as a threat, is pretty simply AWS Nitro system. AWS Nitro system is the underlying platform for all of Amazon EC2 instances. So if today you go and launch an Amazon EC2 instance, it by default, de facto, launches on AWS Nitro system. So to talk more about what AWS Nitro system is, I'm going to hand over to Suresh here.
Yeah, thank you, Sudhir. So on the screen, what you see on the right side is Nitro system. But before we get into the details of like how Nitro system came to be, let's understand the classical system, right? Like traditionally for decades, the classical virtualization is like you have a hypervisor on your host machine, and then the hypervisor need to do many things, right? It needs to make sure that it is providing necessary networking to the EC2 instances, the storage, right? The local storage and the attached storage, etc. And also it needs to do monitoring, like when to launch instance, where it needs to launch instance, what type of instance it needs to launch, and collect metrics, performance metrics, etc. Those kind of things, right? And so that takes up, like the hypervisor on the host takes up memory and CPU and everything, right? So it takes some of the resources from the host machine. And then, after working over a decade at AWS, like, we are continuously trying to think on behalf of customers, how do we get like maximum utilization of the hardware? How do we bring more security to our customers? How do we get like maximum performance, to the customers, right? Like kind of a bare metal type of performance. And during that process, what we did over the course of time is we reinvented how we do virtualization. And that process enabled us, like first we started with the networking isolation. So that's where we started like taking out these responsibilities of the hypervisor away from that host machine. And then as you see on the bottom, you see like we took out from the hypervisor, we took out both networking, storage, all the management functionality into the custom hardware chips, right? The PCIe cards. And then we will talk about the details of like what exactly in the Nitro system. But during that process, essentially, now you can see on the right side from a visual standpoint, like now you can launch more instances because we freed up all the compute and memory that requires by the hypervisor. And then what we left out with a very lightweight hypervisor, right? So we rewrote the hypervisor, what we call it as Nitro hypervisor. And so that responsibility is like, it's a very passive hypervisor. It's just only acted upon. And then in the bottom, that's the isolation we did between the host machine and a separate box, all right? So what is inside the Nitro system? So what you see is like the three main components of the Nitro system is the Nitro cards. These are very custom hardware, like Sudhir mentioned in the beginning, the custom hardware and firmware that to isolate the storage and the block storage, etc., including networking. And then the network security chip that is on the motherboard. The purpose of that one is actually like basically like during the boot up of the host machine, it actually puts the host machine in a reset mode to make sure that only the known hashes of the hardware's firmware is actually booted. So that's what it checks. And if anything changes, then the system won't boot up. So that's how we make sure that there are any vulnerabilities, any non-known state firmware is not loaded, right? And then the hypervisor itself, right? Which is, like I mentioned, it's after we strip out everything from the hypervisor, all the operations that you see on the left side, then it became just, all it's doing is just memory and CPU allocation, right? Then that's how we are able to get bare metal like performance on the virtual machines. So in a sense, now you have the host machine, and then we separated out the box, right? Like where you have the security, networking, and storage, all these are separated, and that is the Nitro system. And then we are able to dedicate more resources, so we are able to get more utilization for ourselves so that we can be more cost effective and pass on those savings, and also able to launch more and more new type of instances much quicker. And then good benefit of like the isolation is actually what is bringing the confidential computing capabilities. And to talk more details, I'll pass on to Sudhir. Before I pass on, you can read more about the Nitro system There's a white paper. You can scan that. We also had it validated our claims through a third party as well that you can find in this documentation as well. And we went even a step beyond. Whatever the security claims that we are making, we actually added to our service terms. That also, no other cloud provider has done something like that. So with that, I would want Sudhir to kind of dive deep into Nitro enclaves and Nitro TPMs.
Absolutely. Thank you. Thanks, Suresh. All right. So hopefully, dimension one of confidential computing and the solution to that, which is simply any Amazon EC2 instance, is clear to you, right? In other words, this is my favorite phrase to say, right? Amazon EC2, we call it always on confidential computing. And the reason we use the term is precisely because of this. AWS Nitro system gives you that isolation, protection, assurance that we, as AWS operator, are isolated from your instances. There is no mechanism for us to get into your instance, even if we wanted to. And that's by design. And like Suresh said, that unless, let me just go back a slide, unless you got a chance to take that QR code, we have elaborated about the security properties of Nitro system in much, much more detail in that white paper, right? So please give it a read. It's a very interesting white paper, at least for me. So now let's move on to dimension 2, all right? So dimension 2 of confidential computing, what was that? It was where customers asked us that give me tools, features, services to isolate my own workloads and go build that trusted execution environment so that you can run your sensitive components, whether it's a microservice or it's an analytics application, inside the TEE, right? So that was dimension 2. The answer to dimension 2 on AWS, there are multiple options. So today, in this session, what we'll do is we'll visit those TEEs, and we'll actually look at how attestation works for them, right? Because the talk is all about attestation, and I want to demystify the attestation for you. So let's get right into it. The first option for dimension 2 TEE is AWS Nitro Enclaves. I'm going to be very, very brief here for AWS Nitro Enclaves because we got to get into the code. But here is what an enclave is. AWS Nitro Enclaves is a EC2 service feature. That's the important bit, right? It's not a net new AWS service that you have to go consume. It's a feature of Amazon EC2. And what it gives you is an isolated execution environment, like I said, so that you can bake your sensitive code and data that you want to protect from unauthorized access into this enclave, into this isolated execution environment, right? So there are certain characteristics that you need to be aware of when it comes to enclaves. But the important thing that I would like you to remember is Nitro Enclave is not a small little container. It is not. It may look and feel like that, but it's a full-blown virtual machine. So you could allocate the amount of resources that's necessary for your workload. You just have to find the right size of EC2 instance, which you would anyways to run the workload on the EC2 directly instead of enclave. So the mental model here is it's a full virtual machine. It's constrained for the right reasons. It has meaningful defaults. It is very opinionated. So what are those characteristics that make it very opinionated? Let's look at it. An enclave does not have EBS attached. If you're familiar with EBS volumes, you cannot attach one to enclaves. What it gives you is a pure in-memory file system. Enclave does not have ENI attached as well, right? So if you want to use your security groups, NACLs to communicate to the outside world, you cannot do that. There's simply no way. It's isolated. It's air-gapped. It's cut off, remember? And there are other properties as well. But the most important property, which is what this session is about, is cryptographic attestation. So what is cryptographic attestation? Well, we're talking about TEEs, trusted execution environment, right? And we are talking about runtime protection. We are not talking about transit or at rest, if you recollect from my opening statement. So the question simply becomes, if I tell you that, hey, I'm running an API, and by the way, I'm running it in an enclave, and let's play with this. Let's say you are a consumer of that API. how would you know at runtime that I'm actually, in fact, running the API inside a TEE versus a simple Amazon EC2 instance? It's not simple, but I'm just relatively speaking, right? That mechanism through which you can attest to the fact that a service or your execution environment, to be precise, is a TEE is called cryptographic attestation. I have a slide for that. We'll come to that later. But let me talk about the second option. Like I said, there are multiple options for Dimension 2 on AWS. There are multiple ways you can bake a TEE. The second option is using a TPM. Amazon EC2, again, has a feature called Nitro TPM. You can enable Nitro TPM on a EC2 instance when you create an army and use the army to launch the EC2 instance. It's in the, it's a simple two-step process, right? You need to have the right TPM drivers, et cetera. But if you're already familiar with TPMs, Nitro TPM is a TPM 2.0 spec compatible feature, meaning any of those Go TPM or TPM tools that you are probably familiar with will just work, drop dead simple, right? But what is Nitro TPM-based TEE? Well, I have a slide on that later. It's a little busy. We'll save that option as a solution towards how you can use a TPM to go build a TEE, right? But the idea is simple. The mental model, just like an enclave, is an isolated execution environment, which is cut off even from the parent EC2. A TPM-based TEE will give you the flexibility, will give you the ability to make an Amazon EC2 instance itself, the entirety of it, as a TEE. So if I speak in terms of attestation, because Nitro Enclaves, I said, has cryptographic attestation, we'll look at it in the code. Similarly, Nitro TPM, because it's a TPM 2.0 compliant feature, will give you the ability to get a TPM quote. TPM quote is used in attestation. We'll look at that later. All right, so hopefully now the two options of attestation is clear. So let's spend some time, excuse me, on what is attestation. I'll take the Nitro Enclaves example. In case of Nitro Enclaves, an enclave has the ability to fetch something called an attestation document. This attestation document is, if you're familiar with document formats, JSON is a very popular one. This happens to be in CBOR. CBOR is concise binary object representation. It's an acronym. The reason we use that is it's lightweight compared to JSON. It's very fast in terms of parsing and verifying, hence why we chose CBOR. But the most important property is this attestation document, regardless of how it's formed or created, is signed by the Nitro hypervisor, right? And what it lets you do, because of that fact that it's signed by Nitro hypervisor, is it enables you to do remote attestation. So if you go back a couple of minutes ago when I said, how do you confirm or verify that the entity or process you're talking to is in fact running in a TEE, this is exactly that mechanism. Remote attestation is through which you can ask an enclave, hey, give me your identity, and then it provides you an attestation document, and that attestation document is what you will verify at runtime to attest to the fact that this TEE has certain properties that are desirable to you. This TEE has some fingerprints or measurements that are known to you, and if you want to proceed further with communicating with this TEE or exchanging data with this TEE, so on and so forth. OK, so enough about attestation. Just one last add-on to this. This is very specific to Nitro Enclaves. AWS Nitro Enclaves has out-of-the-box integration with AWS KMS. What I mean by that is AWS KMS knows how to verify, parse, and consume an attestation document presented by a Nitro Enclave. Right? The reason we did that is to make it easy to consume attestation. It does not mean that AWS KMS, or for that matter, any AWS API has some special privilege or connectivity to the enclave. No. Anything outside the enclave, whether it's AWS or non-AWS, is outside the trust boundary of the enclave. Right? The same should hold true regardless of which TEE option you choose. The same thing should also apply for the TPM-based TEE. So if you're curious, why do we have two options? When to use which? Well, here's the mental model for that. Right? AWS Nitro Enclaves is an opinionated TEE. It has a lot of opinions. It has a lot of meaningful defaults. It has constraints on what you can do or cannot do in terms of disk attach, ENI attach, GPU attach, et cetera. TPM-based EC2, on the other hand, I would put it on the other side of the spectrum, the other extreme end, where we are giving you a tool called TPM so that you can go build a TEE, which can, if you choose to, be exactly same as the enclaves. So you configure it in such a way that you can make an enclave out of it, or you can fit anywhere in the spectrum where you can say that, hey, I'm actually OK with the ENI attach. I'm actually OK with the disk attach because I know how to handle encryption at rest using tools like Lux, et cetera, right? And maybe your workload needs GPU attach. So maybe you're like, hey, I need a TPM-based TE where I want to go launch it on an instance like a G5 or P5E where there's accelerated cards available for me, right? So depending on your workload, depending on your needs, depending on your properties that you desire for the TE, TPM-based TE might be the answer for you, right? But if you want to just get up and running quickly, you don't need all those bells and whistles, enclaves-based TPM, enclaves-based TEE, sorry, might be the answer, right? So that's the mental model. More on that later. Now, what I would like to do is jump into the code, and to put some context around this, we'll take a very simple example, and to talk more about that multi-party competition example or multi-party collaboration example, actually, I'll pass it on to Suresh.
Yeah. So the multi-party in this one. Just let's take a scenario, and this is the scenario that we're actually going to show you the code as well. Let's take a very simple scenario where there is a customer who wants to consume a model, a large language model, or any kind of foundation model. And that consumer needs to know that it is actually really running in a trusted execution environment, right? There is no exfiltration is happening. Like, they need to make sure that, all the code that is necessary to make that is like the customer is actually verifying ahead of the time, right? And the model provider, before they distribute the model to customer environment, they need to make sure that customer is not stealing their IP, right? It is not, they are not making a copy of the model weights and then doing something else, right? Because it is not running inside their environment. It will be running inside a customer environment. So that is the scenario that we want to talk about. So there are two parties here, the consumer of the LLM and the LLM provider themselves, right? So LLM provider wants to protect their IP, which is the model weights, and the customer wants to protect their data, and they want to make sure that their data is not leaving to a third-party model provider. And it is indeed running in a trusted execution environment that even their own administrator cannot see what is going inside, right? So that's a dimension two that we just spoke about. So this is the scenario that I just explained. Customer wants to protect the prompt and the query, and the model provider wants to protect the large language model. Now, how do you do that? How do you accomplish that, right? So the first thing that we do in this case is like the model provider is doing all these activities, right? So they have trained a model, and you have the model weights. What they can do is like they can use KMS, the AWS Key Management Service, and then they can request a data key. Okay, so the data key is used to encrypt the model weights, right? So what they'll do is like they'll take the data key, and they'll take the model weights, the encrypted data key, and the model weights, and then they can put it in an S3 bucket, right? And then what they can do is like they can attach a policy to that S3 bucket saying that only if the only a trusted execution environment can decrypt it, right? So that means like when the consumer is actually launching this model, what they'll do is like the model weights get actually downloaded into the trusted execution environment, in this case, the Nitro enclave. And then inside the Nitro enclave, then only it can be decrypted. Because the data key is also encrypted in the S3 bucket, it can only be decrypted by the enclave. So that's what the KMS policy can do using the PCR values, that which Sudhir will walk into the details. So that's how this can be done. And then what you see is a busy slide, what you see. So I'll kind of walk you through. So you have a network, right, the purple box. And inside that, you have a EC2 instance. And then on the right side, you have a enclave. So the model weights are actually on the top. You can see the bucket where the model weights and the data key is encrypted. And then it has a policy that it can only be decrypted inside the Nitro enclave. And from a customer standpoint, like customer who is actually accessing this model, they can actually attest to that it is actually indeed the trusted execution environment before they actually send the query. So these are the two things that we will see in the code. And then he'll in the code explanation, I think it will get more clear on all the what are the different proxy calls out there and how the model weights are encrypted, et cetera. So since it's a code talk, let's dive into the code details, and then you will see all of this in the action through the lines of code.
Cool. Awesome. Thanks, Suresh. All right, let's jump right into the code. I'm going to switch screens here for a second. Excellent. All right. By the way, we're going to look at two pieces of code today. One, the very first one up on the screen, is all about attestation. Right? I'm going to show you how the attestation APIs look like in code. We'll use Python. By the way, we'll keep it very, very simple. It's like a hello world. And then the second piece of code is going to be what Suresh just talked about. It's going to be a multi-party collaboration example with LLMs. We'll look at that code as well. Right? And if you want to follow along, all of these code samples, I would say grab this QR code. If you want to, this is a link to a GitHub repository where you have the entirety of links for today's session and beyond, right? So take that, and then I'm going to switch over back to the code example here.
Is the code visible? Anybody wants a bit more zoom in? Is good? OK.
All right. So the way we have structured this is Nitro enclaves. This is going to be the first TE is what we'll look at in this code, right? It's a TE based on Nitro enclaves. Nitro enclaves, the way it typically works is you partition your code, you separate your code. You don't have to necessarily do it, but assuming that there are only certain parts or components of your workload that are sensitive compared to the others, the mental model is you separate out the little microservice or larger monolith that is sensitive that you want to package into an enclave into something called a server for the purpose of this example, right? And then the remaining portions of your workload is what will run on the EC2, which in this case is called the parent EC2. That's the client. So I've arranged the code into two folders, client and server. And the build experience or the development experience with enclaves is pretty straightforward. What I'm going to do is, let me zoom in this code a little bit. What I'm doing here is Nitro CLI. Nitro CLI is an open source command line interface. It's a tool that we open sourced. It's in the links that I shared in the QR code. That is the one-stop shop pretty much for Nitro enclaves. You can use the tool to build enclaves, launch enclaves, terminate enclaves, pretty much cater to the life cycle of the enclaves, right? Here, what I'm doing is I'm taking a small little hello world example, containerizing it. Containerizing the application that you want to run inside an enclave is a prerequisite if you use Nitro CLI. There are other ways to go build an enclave beyond this talk, but please go browse those documentation links, right? But as far as Nitro CLI goes, it's a two-step process. Containerize your application. So in this case, what I'm doing is I'm doing simple Docker build, right? And I'm taking what's inside my server. I'll show you what's inside the server. Inside the server, what I have is a Rust application. There's no opinion on what can run inside an enclave. It can be any programming language. Anything that runs on a Linux operating system is OK here, right? The default operating system that we bundle with is a Linux kernel inside the enclave. So what I have here for the purpose of attestation is a small little program called attestation document retriever. Since this is written in Rust, the first library that I'm using here is called NSM API. NSM stands for Nitro Security Module. NSM is a device, emulator device, only available inside an enclave. You cannot do any of these attestation API calls outside of EC2. Because if you recollect, it's a special property of TE of an enclave, right? So I'm using NSM API here. And the API to retrieve an attestation document, if I can find it here real quick, is get attestation document. And that API takes 3 inputs. A public key, a nonce, and user data. Right? The reason you have public key, a little theoretical aside, is every enclave, as part of the attestation document, can embed a public key inside the document itself. The relying party, or the party which receives this attestation document, when it wants to send sensitive data or code only to be used by this enclave, can use the public key to encrypt that information. Right? So that's the reason for public key. Nonce, you might be familiar with it from sessions, et cetera. Nonce is just to ensure the attestation document is not stale, it's freshness. Sometimes it is also used to mitigate replay attacks, just so that you know, hey, the client sends a nonce, the server replies back with something, including the nonce. So that's how the client knows, hey, it's talking the same language, it's talking the same session, right? So that's nonce. And user data is, it's user data. It's a section in the attestation document that you can use to embed certain things specific for your application, right? A lot of use cases there. But end of the day, NSM API is what you will use to send these 3 inputs when you request an attestation document, like I'm doing here in the code. And in the response, you get back the attestation document, base64 encoded. End of the day, it's a CBOR document, right? So all my server is doing here is getting the response, getting the attestation document in the response, and sending it back to whoever is calling this. That's it. Now, if you go to the client, now client's responsibility. Let's talk about cryptographic attestation, right? Imagine client is a consumer of an API who is trying to ping the API running in the server, and part of the handshake, the server is responding back with the attestation document that we just looked at, right? It's a CBOR document. One of the primary responsibilities of the client is to verify the attestation document. That is precisely one of the things that I'm doing in this client.py, in this Python program. Verification of attestation document is done using a couple of things. One is called semantic validation. Semantic validation is where you ensure the integrity, the structure, the schema of the attestation document is intact. Meaning, in other words, it's a valid attestation document because the attestation document has a schema. As simple as that. The second step, this is the most important step, is every attestation document, I said that again, I'm going to say this again, is signed by Nitro Hypervisor. The PKI infrastructure behind that signing process, the root certificate to be very precise, is something we have made it public because for the right reasons, you would want to verify the signature, right? It's available on an S3 bucket. What we use for the signing process is ACM PCA, 2 acronyms. If you're familiar with it, it's Private Certificate Authority. It's a service. The service is called ACM. And there's a way you can get private certificates out of that ACM. They're typically valid for 30 years. So an enclave's signing certificate is valid for 30 years. It's available publicly. So that's exactly what I'm doing in this code. I'll show you. I'm verifying the signature of the attestation document. Once I do these 2, and once I know that it's a valid attestation document and it is signed by Nitro Hypervisor, then I can proceed to parse the attestation document and get to something called PCRs. I'll show you that. All right. So Let me just quickly collapse the code. All right. So here, my client Python program is initiating the connection with the server over something called VSOC. If you're familiar with socket-based programming, VSOC is also called as Word.io VSOC. The address family is AF VSOC. It's not something AWS has invented. This was done by Red Hat. It's already upstreamed into Linux kernel. So this is not new. You probably already have the drivers to talk to AF VSOC sockets in your operating system already, right? So what I'm doing here is, and by the way, if you're curious, there are only a bunch of languages that are that have the native language bindings to talk to a VSOC-based socket, right? So if you happen to use something like Java, you have to fall back onto native integrations, run native code written in C, C++, or run a binary. You have to do some sort of foreign function interfaces in those non-supported language. Python, luckily, for this purpose of the demo, is one of those languages that supports VSOC. So what I'm doing here is I'm opening up VSOC, and I'm sending a nonce, right? Let me just get to that. Nonce right here. I'm opening up the VSOC, and I'm trying to send the nonce to the server. And then the server, you looked at the code, all it's trying to do is fetching an attestation document with the inputs that I have given to it. Important point here is, if you recollect, public key was one of the input to attestation document, API. I am not sending the public key because my client is outside the enclave. Client is outside the trust boundary. All the client is doing is, hey, I want to talk to a TEE. Give me your attestation document so that I can verify you are the right TEE. And just to make sure I'm mitigating replay attacks, I'm sending you a nonce. That's all, right? So this client.py is simply sending a nonce, receiving an attestation document, and then I'm trying to do those two things that I elaborated, right? Your semantic validation and then verification of the signature. So where I'm doing that here, just so that you get the sense of code, is right here. As part of verification of attestation document, we'll get past the semantic validation, which is, hey, does it have the necessary fields that I need, which is PCRs. PCR, another acronym, is Platform Configuration Register. So when it comes to TEEs, you just have to remember this. This is like the thumb rule, right? You will measure certain things about TEE, and then you verify those measurements. That's how you know your TEE hasn't been tampered with when it was built compared to when it is running. That's the whole point of a TEE, right? Your execution environment, you want it to be stable, not tampered with, integrity intact, et cetera. So measurements are key. PCRs is just another name for measurements, for hashes. In this case, in case of enclaves, we are using SHA-384 as the hashing algorithm. So you have SHA-384 hashes, which is what you will check for in the attestation document after you verify. So in the verification process, I'm downloading the root certificate, and then I'm verifying the certificate chain that is included in the attestation document is intact, right? So there are 4 certificates to be very specific. Each one of them, if you look at the details of the certificates, corresponds to something like the instance itself, the AZ, and the overall region, and then it just bubbles up from there, right? So there's 4 levels of geo hierarchy, if you will, and we are attesting to the fact that it's exactly the same, right? The instance in the AZ, in the region, et cetera. And then, of course, the final certificate, the leaf node, corresponds to the enclave itself. So there will be a common name on the certificate which literally tells you instance ID, hyphen or underscore, enclave ID, right? So you get the idea. You're trying to pin it all the way down the hierarchy with using these multiple certificates, and then you have the root certificate that you use to validate this entire chain. So that's exactly what I'm doing here, using just off-the-shelf tools. In case of Python, I'm using a library called cryptography. And once I'm done with validating the signature, I'll move on to consuming the PCRs, right? Now I know semantic validation is done, the PCRs are there, the nonce is there, my user data is there, and the signature is valid. So now I'm actually OK to go parse the PCRs, which is what I'm doing here. And PCRs, one of the property, you probably know this if you are working with TPMs, is the value of a PCR when you mutate it is not getting overwritten. It retains the history. In other words, if I give you a PCR hash, the way you arrive at the same hash is, I'll give you a naive example, right? So let's say if I'm telling you that, hey, my TEE is running Llama 7B. Llama 7B is the LLM that's inside my TEE, and that Llama 7B happens to have a GGUF file, just terminology, but at the end of the day, you have a file, and you can measure the file. So I do a SHA-384 hash of the file. I'll take the hash, and let's say I decide to put it in one of the PCRs. The operation is called extending. You're not overwriting. So whatever value was there previously, combined with this new hash is what results in a net new hash, net new measure that goes in the PCR. The reason we do that is if you want to know whether the asset or artifact that you're trying to measure has been tampered with, you get a net new hash that's different but inclusive of all the previous states, if that makes sense, right? That's how you know something has been tampered with. Because if you simply had the ability to overwrite something, you would just overwrite it and say that, hey, my client recognizes this particular PCR. Why don't I spoof the PCR, right? You get the idea. So once I verify the attestation document, I move on to PCRs, and then I'm moving on to further attributes like nonce. We talked about nonce. And then finally, timestamp. There is a notion of a pseudo TTL. I'm not calling it as a TTL because there's no attribute called TTL on the attestation document itself, but there is certificates. Those certificates have expiry time. On top of my head, I think it's about 3 hours, give or take. So if you have an attestation document that is valid, but it has an expired certificate, go ask for a new attestation document, right? You want to verify that it is still fresh, in other words. All right. So you get the idea. So this client.py is going through all the steps that you would have to do to verify an attestation document presented by a TEE. The attestation document has certain interesting properties like PCRs. End of the day, you live and breathe PCRs, right? Your TEE is PCRs for you. Your TEE has to be measured, and your number one responsibility as consumer of the TEE or a component that talks to the TEE is to make sure those measurements are known measurements, right? So essentially, my client.py is going to get to those PCRs, and then I will do a simple check saying that, hey, if PCR 0, I know I haven't introduced you to what those PCRs are, but PCR 0 is a measure of the entirety of the enclave. So even if any single bit of code changes between the kernel, the operating system, the kernel flags, command line parameters, initramfs, finally your application, any of those change, the PCR 0 is going to change. And it's a one-way hash function. So there's no way you can reconstruct it unless you know the original components that went into it, right? So my client.py has to confirm that the PCR is a known hash that it can trust, and only then it will proceed to consuming the service process or what have you that's running inside the TE. Hopefully that's clear. Everything else in this example is just, I would say, logistics behind consuming CBOR. I know I mentioned that this attestation document has a data protocol, serialization protocol called CBOR. So you use a library to marshal, unmarshal between CBOR to JSON to strings, right? But that's about it. Now let's look at the build experience. Back to how to consume this. Nitro CLI takes a prerequisite, which is a container image. So the first and foremost thing that I'm doing is I'm taking my server, all the code inside this server, and building it, right? So Rust has its own tooling on how to build and arrive at a Rust binary. That's exactly what I'm doing here. And then I'm using Docker build as my packaging mechanism. Out comes an image, right? That is the image that I'll use in the next step to go build an enclave. Here, what's noteworthy to call out is pretty simply Nitro CLI. Nitro CLI has a command called build enclave. It takes the Docker URI or whichever registry your Docker container is posted to in the previous step as input. As simple as that, right? And the output of this build command, build enclave command, is simply a EIF file. EIF, an acronym, stands for enclave image file. Enclave image file has its own image specification. It's in the links that I've shared with you earlier. Take a look at that. There is a certain, that image specification will help you understand the headers, the sections within the enclave image file, how the simple init process works within an enclave. Because like I said, enclave looks like a container, but it's not. But there are certain things that are container-like. The number one thing you probably want to know is inside the enclave, you can only run one process as part of the init as your PID1. You cannot, well, you can still run processes in the background, but the idea that I'm trying to paint is just like container, there is this notion of you do the bootstrap and then kick off with just one process, right? Just keep that in mind. In other words, there's no systemd, and that's on purpose. We kept the init process very simple. That init process is there in the image specification as well. All right. In interest of time, I'm then just going to move, right? So you will see that the theme repeats. Nitro CLI, like I said, caters to the entire lifecycle. So I have used it for the build. You will see that I'm also going to use it for launching the enclave. So launching the enclave is in run server.sh. It's a simple shell script. All it's doing is it's terminating any existing enclaves. By the way, if you're curious, you can launch up to 4 enclaves from a single EC2. So what I'm trying to do is just clean up anything existing, and then I'm launching the enclave itself. Now, the important thing to note here is when you launch an enclave, this is the options that you have. You can choose how much vCPU and memory you want to donate to this enclave, right? That is one of the configuration parameters that Nitro CLI accepts as part of the run enclave experience, right? So that's exactly what I'm doing here. I'm saying Nitro CLI, go launch this enclave for me. Here is the EIF file. Here is the CPU count. Here is the memory. And by the way, with VSOC, you get a couple of things that you can read upon. Just like IP addressing scheme, you have IP address and port. VSOC has context ID and port. Context ID and port is what you will use as your addressing scheme when you talk to an enclave or an enclave talks to the outside world, because that's how you navigate the VSOC channel, essentially. OK. Just one last thing. There is something called debug mode when you launch an enclave. This is purely for development and testing purposes. So if you are curious to know what's happening inside the enclave, what you get out of debug mode is the standard out. Whatever is being printed to console inside the enclave will be piped out to your console wherever you are running this command. The only reason I bring that up is how do you identify when it comes to attestation whether the TEE is running in debug mode or production mode? Well, the answer is very simple. If PCR 0, which is the entirety of the enclave, the measure of the enclave, or PCR 1 and 2. PCR 1 and 2 are also measures of little different things about enclave. PCR 2, most importantly, is a measure of your application code. So anything that you containerize, in this case, that simple Rust application, that results in a PCR 2 hash. So these PCRs, when you run an enclave in a debug mode, are all zeroed out. That's the number one indicator that you're talking to a TE in debug mode. In other words, you probably don't want to unseal your sensitive data to something that's running in debug mode, right? That's purely for development and testing purposes. So that's one thing I'll call out. And the rest of the code is pretty simple. All I'm trying to do is launch an enclave, and then finally just describe the enclaves. Describe enclave is just to spit out some metadata about the enclave that's running right now, currently. So that's about it. That's a simple code, a hello world example. This, by the way, is available on those links. We posted a repo called, if I can get to it, AWS Nitro Enclave samples. This exactly is there. How to consume an NSM API. There are a bunch of other examples there as well. So if you want to go try it out. All right, so that was demystifying attestation. Attestation document, what are the fields in it, how do you consume the NSM API, and most importantly, how do you verify before you consume the PCR values? Because like our talk says, you want to measure and verify your TE. Otherwise, there's no point in consuming a TE. You're just blindly trusting whoever you're talking to. So hopefully that grounded you in attestation primitives. Now it's time to move on to the next example. For that, I'm passing on to Suresh.
Yeah. So now that you understand how the attestation process looks like in the form of code, I briefed you on that example of like an LLM provider and a client, and this code actually kind of walks you through that. So this is basically an extension of what Sudhir actually showed, but with a real-world use case where we are, creating a, data key from KMS and then encrypting the model weights and then putting it into an S3 bucket and then and sealing them. What do we mean by sealing? Making sure that it can only be decrypted in a trusted execution environment that matches with the PCR values that Sudhir just spoke about, right? Only can be unsealed, and that's the key, right? So that actually guarantees the runtime guarantees. Like I mentioned, some folks who missed the beginning, this is about runtime, security guarantees, right? So let's get into the details.
And by the way, this example you can follow. We posted this as a workshop, which you can run. Obviously, the experience is going to be a little bit different. This is all scripty because it's a code walkthrough. The workshop has much more streamlined. You'll get right into sealing and unsealing, those two actions that Suresh was talking about. He's going to show.
So it's similar to the previous example. In this case, the server is where the code where it the code inside the server is what we are kind of planning to package inside the Nitro enclave, and we have a Docker file. The first step is to build the application Docker file, and the build application is exactly doing that. It is taking a base image and then creating what called LLM server. And in this case, what you see here is like the Docker base file. It has all the dependencies that it actually requires. As you see, like just primitive base Linux image, and then installing lots of dependencies that it actually requires. There's nothing special in the base image, but in the Docker file, this is what gets built from the base image. And in this one, what we are doing is like we are building, the Ollama installation. Ollama is basically a inference library that helps you to host an LLM. In this case, like a LLM in the format of a GGUF file. So that's what we are doing here. So that once the application is built, then the next step that what we are doing is basically, so if you see in the README file, like the envelope encryption model shell file. So that is here. What we are doing in this one is basically using KMS. We are getting a data key, and then we are basically getting the encrypted data key into this particular file. And then we are also getting the plain text format of the data key. And then using the plain text format of the data key, we are actually encrypting the model weights. And here you can see the API key is inside the encryption key is inside this one. And then we are taking the model weights that are downloaded and then encrypting with that key. And then finally uploading the encrypted data key and the encrypted model weights that is encrypted using the data key. And all these files are basically uploaded onto the S3 bucket, right? But now, how do you make sure that you are sealing it, right? You need to make sure that you update the KMS policy that it can only be decrypted inside a Nitro enclave. So that is the next step. So if you see, like before we go into that sealing part, let's go into the building the enclave part, so which is basically taking the container that we just built and then making sure that we are actually building a EIF file. So that is going into the build enclave one. So let's go into see that. And what you see here is very similar to what Sudhir showed earlier. And we are using the same Nitro CLI to build the enclave. And one important thing that you should, these three things are already kind of mentioned in the previous example. What we are looking here is basically like providing the certificate as part of the measurement, so that that certificate will be distributed to the client, that the client can actually verify that it is indeed that particular image. And here we are finally just building the enclave EIF file. So there anything to add here?
Yep. It's the same primitives, right? By now, you probably noticed that we are still using Nitro CLI. We are still using the same build on-curve primitive. You should get the idea by now that beyond the basic PCRs, beyond the basic measurements, you still have the capability to measure characteristics of the TE that are important to you, whether it's an application code, whether it's a measure of a configuration file, et cetera, and then use NSM API to extend a higher order PCR, anything that's above, let's say, 16. You got 32 PCRs in total at your disposal. Use one of the PCRs to extend the hash about things that are interesting to you in the TE, and then verify and attest to them. In this case, what we're doing is we are measuring and hashing the LLM model weights, because I want to know that A, I'm talking to a TE, B, the TE hosts my LLM server, and C, it is serving a very specific model to me, not just a general LLM, right? Maybe it's a specially tuned LLM, fine-tuned LLM specific to my domain, right? So you get the idea. The primitives remain the same.
Yeah.
You're about 2 minutes.
Yeah, so we have 2 minutes. Just want to quickly run through the complete example. So here is where the fourth step, we are sealing the model. So you can see like the KMS policy is updated, that it can only be decrypted that matches the KMS policy that we have created. And then finally, like the client is the one that which is very similar to what Sudhir has spoke to in detail in the previous one, making sure that it is checking the right PCR values are there, and then only it actually makes the request to the model in this case.
And all the busy lines of code that you see there are just proxies. So if you look at the architecture diagram, and again, it goes back to the fact that your TE, depending on your use case, restricts the network access to the outside world for right reasons, right? So in case of Nitro enclaves, to be very specific, anytime that you want to talk to an external service, which is pretty much anything that's outside the enclave, you got to go to the VSOC channel, hence the need for some code that can adapt VSOC to INET and vice versa, right? So in this example, in this case, in the workshop as well, what we have done is we have decoupled the VSOC to INET marshalling and marshalling using adapters. We used a pretty popular open source tool called SOCAT. You can write your own adapter as well, but the idea is to decouple my application code from the adapter code, from the bridge code, right? It's just a design pattern that we chose to use.
Yeah. So from a visual standpoint, this is the one, right? Like you can see the VSOC in the middle, right, between the host machine and the enclave, and those are the things that you are actually seeing here in the code.
Cool.
With that, we have 2 minutes. Any questions you can take?
Yes, please. So the question is there any part of the EIF file that's not measured or attested by PCR0? Well, EIF file, again, this is in the image specification as well. PCR0, yes, it measures the entirety of the enclave image, but there are certain section headers between components of EIF. I think we probably have a visual as well in the image specification repo. There are certain things that does not make sense to measure, right? Because it's like measurement about measurement. For example, if there's a EIF section and then there is a signature for that EIF section, you probably don't want to double measure it, because the signature is attesting to the fact that what it's signing is not tampered with, right? So yes, there are some nuances, but from a practical purpose, yeah, the idea is PCR0 just caters to the entirety of the enclave image file. Good question. Yes?
Just confirming that Nitro CLI is separate from the AWS CLI that you use for the rest of
That's correct. Yes, the question was, is Nitro CLI a separate component? Absolutely. It has nothing to do with AWS CLI. Nitro CLI is something that we have written very specifically for Nitro Enclaves, and we have open sourced it. But the reason we did not call it Nitro Enclave CLI and just Nitro CLI is the idea is it should cater to all the TE options on AWS, right? Not just enclaves. It just happens to have subcommands that are enclave specific, right? But yes, it's a separate piece of code. And it's open sourced as well, so there's a GitHub repo for that.
Yeah.
And again, if there's any questions, our contact details are on the last slide. Please reach out to us, and most importantly, let us know what else you would like to see in a talk like this. The idea behind this talk was to just deep dive right into attestation. We just spent a few minutes on introduction, just so that we are all on the same page. But if there's one thing that you would take away from this talk, it would be this, right? On AWS, there are multiple options to build your TEs. Enclaves just happens to the first one that we have launched. It's an opinionated TE. The other TE, the TPM-based, Nitro TPM-based TE is probably what gives you the most flexibility as of right now. That is generally available. The only prerequisite is you just need to find an instance where both enclaves and TPM are enabled. And the reason for that, real quick, it will take a full hour to explain that, but the reason for that is TPMs, if you're familiar with it, they support attestation, but they do not support remote attestation on AWS. So we use enclaves in that architecture, in the topology, only to support remote attestation. Otherwise, in a TPM-based TE, the entirety of your workload is running on the host CPU, not inside the enclave. Enclave can just come and go just to support attestation, and that's about it. And that's the reason why you could go build your accelerated compute workloads like LLMs, et cetera, on TPM-based TE, whereas it may not be possible on Nitro Enclaves-based TE if you want GPU-based inferencing. It is still possible, because we just showed you an example where we're actually running it on a CPU-based instance, where the idea is maybe for your workload, CPU inferencing is enough, right? So that's what I would like to leave you with. And again, thanks for joining this talk. It's probably not one of those super high-level talks. It's probably a lot of boring details, but these are very important boring details, at least in my mind. So thanks again.
Thank you all.